Hello, everybody. I'm Manoj. I'm part of LinkedIn's data team for last 2 years, and before that, I was in PubMatic's data team for 4 years. I have done my MTech from IIT Bombay. With me is Arpan. He is a colleague at LinkedIn. So today we are going to talk about tuning. This is an automated framework to tune Hadoop and Spark jobs. This framework deals with configuration tuning. We do not deal with any of code tuning. So LinkedIn's vision is to create economic opportunity for every member of the global workforce. And our mission is to connect the world's professionals to make them more productive and successful. So today's agenda is we will start with why tuning framework or auto-tuning is needed. Then we will go into details of how does tuning framework works. And we'll cover in detail about architecture and some of the features of the framework. And finally, we will conclude with what future features that we are working on. So let's look into the grid scale at LinkedIn and look into the contrast between 2008 and 2018. So we have like 10 plus clusters now. We have thousands of nodes, thousands of active users. We are using different frameworks like Pig, Hive, Spark, TensorFlow, and we have around 10,000 of workflows. So to do tuning at this scale, it is very difficult to do it manually. So before we go into details of the tuning framework, let's look into the typical conversations that happens in data team at LinkedIn. So manager will go to the developer and say that, hey, this Spark job is running slowly, and it is, for last few days, it is missing SLA of 4 a.m. Can you take a look into this? Developer says that, okay, let me look into the configuration of this job and tune in to reduce the execution time of this job. He goes and tries different configurations, and after two days, he comes up and with an optimal configuration, which makes sure that this job is running within SLA. Another conversations that do happen with Hadoop admin and managers, like Hadoop admin comes to manager and says that we have found few jobs which are taking high resources and owned by your team. Can you take a look at those and optimize those jobs? Manager will say that, okay, let me take a look into this and I will ask my team to tune these jobs to reduce the footprint on clusters. Another very common conversation that happens, that client comes to the developer and he says that this report I'm getting every day at 9 o'clock. I have to present it at 8:45 meeting. Can you can I get this report at 8:30 a.m. or something? Developer says that, okay, I'll try to tune this job to reduce the runtime. So tuning is an integral part of any data team at any of the companies. We do require to tune the jobs because we know that default cluster configuration are not always optimal. So all the jobs are different. Like some of the Spark job might have high memory requirement, some of them might have low memory requirement, or maybe some MapReduce jobs produce high map output records, but other might produce less map output records. So all jobs are different and require a different configuration to run it in a better way and utilize the cluster better. So optimal parameter configuration always leads to better cluster utilization, as well as it reduces the execution time of the job. So there can be many ways to tune the job. Manual tuning is one way to tune the jobs. This is a iterative process of tuning. We start with executing the job, observe the execution and execution metrics of the job. So by metric, I mean the counters of the job. Based on those counters, what we look into, we come up with some kind of configuration and try to repeat the execution with that configuration. So maybe like look into a case where one of the Spark job have average task time very high. So you would like to increase the shuffle partition. Or if it is average task time is very low, you would like to decrease the number of shuffle partition. Or maybe look into other use case like for a MapReduce job, if your ratio of spooled records and map output record is high, you would like to increase the sort buffer so that there is less spill. So these are some of the configuration that user can come up based on looking on the matrices and the counters of the job. So basically, the problem is manual tuning is a time-consuming process. We have seen in practice that it takes around 2 to 3 days to tune a Spark or Hadoop job. And it also needs expertise. User need to know in and out of Hadoop ecosystem, like he need to know job history server, counters, different parameter, what is the impact of those parameters, what is the interdependence between those parameters. So he needs a lot of expertise to tune those jobs. Another thing is, whenever you are doing tuning, you normally will run with the full data, because if you run it with sample data, it doesn't make sense in most of the cases. So when you run with full data, and if you do 10 to 15 iteration of the job to tune that job, it required extra resources on the cluster. Another different way to do tuning is using the Dr. Elephant heuristic-based tuning. So Dr. Elephant is an open source tool developed by LinkedIn. It is a performance tuning and tuning tool, performance tuning tool, where it suggests recommendation based on predefined heuristics. So one of the use case might, like, if your Spark job's peak JVM usage is pretty less than executor memory, it will suggest you to decrease the executor memory. Or if your average mapper time for the MapReduce job is less than a threshold, it will ask you to increase the split size. So these are some of the recommendations that Dr. Elephant gives. In this case, user does not need to worry about hundreds of counters and parameters, but this also relies on users' initiative to use the recommendation. And here also, we expect some kind of user expertise where user can look into the Dr. Elephant recommendation report and come up with the next set of parameter and try those parameters on Hadoop clusters. So this is one of the screenshots of the Dr. Elephant where it is showing one of the application and different heuristics of the that application. Like Spark configuration is one heuristic, executor peak unified memory is another heuristic. The red ones are critical or Seaver. If you look into like executor JVM use memory, this is critical. And if you click on those, you will get a suggestion like this, where it says that your max peak JVM use memory is less than your executor memory. You should try to decrease the executor memory. So looking into this, manual tuning as well as Dr. Elephant heuristic, it requires a lot of effort from users to do the tuning. At LinkedIn, we have 10,000 of jobs to tune. To tune those manually or using Dr. Elephant will require a lot of effort. If you use auto-tuning, your developer productivity will increase. He can focus more on other important work rather than tuning the job. Using tuning framework, it is just like enabling the tuning, and then tuning framework can take care of tuning your job and come up with the optimal configuration of the job. It doesn't require any extra effort, and there is no expertise expected from user, because user doesn't need to do anything. It also provides you an objective functions, like you can tune it for resource usage or execution time, any of cost function you can use it for. So here I will hand over it to Arpan. Let's auto tune.
Thank you, Manoj. Hello everyone, I am Arpan. I work as a software engineer at LinkedIn. I'll talk about TuneIn, which is a framework we developed to automatically tune the recurring Hadoop and Spark jobs. So recurring jobs are the ones which are executed in a scheduled fashion. For example, they can be executed hourly, daily, or weekly. I'll go into the algorithmic details of how in each of the scheduled executions, the framework tries to move the configuration of these jobs towards the optimal value. So at a very high level, it looks something like this. There's a framework in place. There's a tuning framework in place, and there's a scheduled job. Every time an execution happens, a parameter request goes to the framework, which responds with a parameter suggestion. This suggested parameter, along with the job, goes to the executor, and the execution happens. Once the execution is done, the framework collects some feedback about the suggested parameter. I'll showcase how we reduced the resource usage up to 35% of some production jobs in our cluster. So let's start with the optimization algorithm. We use particle swarm optimization algorithm for the tuning process. What PSO essentially does is it tries to mimics the behavior of a swarm of birds trying to search for food particle. I'll try to give you a feel of what the algorithm is before going into further details. So let's assume that this floor is a search space, and there's a food particle exactly where I'm standing, and the objective is to find the food particle using the PSO algorithm. So what it will do is it will start by placing some birds or particles, as we call it, in the search space. Each of these birds will compute their distance with the food particle, and they'll share the information. So each one will know that which ones are in good position and which are in bad position. And using this information, they'll try to move toward a better position, which is closer to the food particle. So this GIF actually very well represents the working of PSO. As you can see that there's a two-dimensional search space. The color represents the value of cost function at each point. The scale on the right maps the color with the value of cost function. I'm not sure whether it's clearly visible or not, but yellow represents the 20 as the cost function value, and the violet region, the minimum, is the -5. So what basically guides the movement of these particles of the birds? So there are 2 points of attraction. The first is the particle's best known position, and the other is the entire swarm's best known positions. So these 2 positions basically guide the movement of all the particles. So as you can see that all the particles which are doing the search process are converging to the violet region, which is corresponding to the minimum possible value of the cost function. So a natural question which follows is why we chose PSO and not any other optimization algorithm. Well, the cost function which we are trying to optimize for, that is the resources a job execution uses, is quite noisy. In the sense, if you execute a job multiple times using the same parameter configuration on the same input data, you will see that the resources used has a significant variation. I'll come to the formula which we use to compute the resources which our execution uses in a while. But what we saw was that there was a significant variation in the resources used by each of the execution. But this algorithm is gradient free and it is robust to noise. In fact, what we found in the literature is that noise actually helps this algorithm avoid stucking at the local minima. The other reason was Hadoop and Spark. These systems are quite complicated to understand completely and write the logic to optimize for. But this algorithm is a black box optimization algorithm. It does not really care about the details of Hadoop and Spark. We experimented with quite a few algorithms which satisfy the above 2 criteria. And what we found was PSO gives us the fastest convergence. I mean, in the interest of the time, I'll not go into the details of all the algorithms which we experimented with, but if someone is interested, we can definitely take that offline. So, I mean, having fixed the algorithm, I'll come to the algorithmic hyperparameters which need to be set before starting the optimization process. The first hyperparameters is the swarm size, that is the number of birds or the particles doing the search. So the ideal value of swarm size should be n-1, where n is the search space dimension. For example, if this room is a search space, then this is a 3-dimensional and this is 3-dimensional search space. So the ideal value of the swarm should be 2. The reason being it guarantees that the particles does not get stuck in a hyperplane. But what we found was that the swarm size of 3 gives us the best result. The reason was, first, 3 is not too small to cover the search space, and it was not too big to do too many random searches. What I mean by that is, at the start of the optimization process, the algorithm places particles at random positions, each of them compute their fitness. They share the information and then the optimization process starts. So essentially, before the first piece of information is shared, the entire searching is random, and we wanted to minimize that. So that is why we chose 3 as the swarm size. The other hyperparameters is that it is really important that the initial position of all the particles at the start of the optimization process, they're evenly scattered all over the search space. This is to ensure that we reach the global minima and not get stuck in a local minima. Okay, so having talked about the cost, having talked about the algorithm and its hyperparameters, I'll come to the cost function of the optimization problem. So we use resource usage per unit input as the cost function. It is computed using this formula, that is summing up the product of container memory and container uptime across all the containers and dividing it by the input size. So this is essentially an estimate of how much memory is being used for how long and dividing it by the input size. So the rationale behind dividing it by the input size was that we wanted the cost function to be input size invariant. Basically, we do not want the goodness of a parameter configuration to be dependent on how much the input size it ran with. So since the numerator had a dependency on the input size, we tried to normalize it. Coming to the search space of the optimization problem, the parameters being tuned actually constitutes the search space. For example, I'm tuning 6 parameters, so the search space will be 6-dimensional. And the parameters to tune depends on the cost function metric. For example, as I just mentioned, that we are using resource usage as the cost function. So we are tuning a bunch of parameters. If somebody else wants to tune for, let's say, execution time, there'll be a different bunch of parameters to tune. So your parameters to tune depends on the cost function metric. I'll talk about the parameters which we are tuning with cost function as resource usage. So these are the list of parameters which we are tuning for Pig and Spark. These parameters were chosen empirically. We only wanted to choose those parameters which have significant impact on the cost function. As you can see, these parameters are mostly like container size and the course. We also have some constraints on the search space. So these constraints are put in place with 2 objectives. The first one being, we essentially wanted to avoid the regions in the search space which can potentially cause failures. And the other was to narrow down the search space to speed up the convergence. So the first type of constraints that we have in place is the boundary constraints. These constraints gives us the minimum and maximum possible value which a parameter can take. So the first, so for instance, we have a constraint on executor course that it can take only values between 1 and 10, both included. The second type of constraint is the interdependent constraints. These constraints capture the interdependence among the parameters. For example, one constraint that we have in place is that the sort MB should be less than the 60% of the map memory. How we derived these constraints? From experimentation. What we found was the parameter configurations which do not follow these constraints either lead to inefficient execution or they just cause failures. So we have talked about algorithm, its hyperparameters, the cost function, the search space, and the search space optimization. There was one more thing that we were concerned about, that it is undesirable that we squeeze memory so much that the execution time shoots up. We did not want that to happen. So what do? We slapped those parameters. We slapped those configuration set. So we updated the cost function. We added a penalty component to it. So now anytime a parameter configuration exhibits this behavior, the framework will penalize it. Talking about convergence, how much time does it take to reach the optimal configuration? Well, there's no theoretical bound on the number of steps that are needed to converge, but what we found was in practically 20 odd executions, these parameters converge to an optimal value. And once that optimal value is reached, we turn off the tuning and we remember the optimal value. And in all the subsequent executions, we recommend the optimal parameter set. These are the results which we got. So for Spark, we reduced the resource usage from in the range of 30% to 40%. This is from the POC which we did. For Pig, we were able to reduce the resource usage in the range of 20 to 35%. And this is from the production cluster. These jobs, the Pig jobs which I'm talking about, are running in production right now in LinkedIn cluster. I'll request Manoj to explain the architecture and the future roadmap of the project.
Thank you, Arpan. So This is the architecture of tuning framework, how it connects with other Hadoop ecosystem components. So tuning framework basically resides inside Dr. Elephant. So Dr. Elephant is again already a open source platform, and the tuning framework is also part of open source. So Dr. Elephant has a component called fetchers, which is different for MapReduce and Spark. There are these fetchers. The job of these fetchers is to get the matrices from Hadoop job history server, resource manager, and FS logs. They pull the matrices from these components and try to compute predefined heuristics based on those matrices. And once the heuristics are computed, these are pushed to MySQL server. There is a REST API on top of these matrices as well as the heuristics. So all the heuristics are basically exposed through these REST APIs. There is another API which is called get current run parameter, which is for integrating with the tuning framework. So as we know that all the tuning is done during scheduled runs only. We do not need any extra runs to do the tuning. So we need to integrate with frameworks like Azkaban, Uzi, and Airflow, which actually runs the job, which are like workflow orchestrator tool. So to integrate, we just need to implement an API called get current run parameter. So let's say if Azkaban is running a big job, it need to call that API to get the suggestion for that execution and run the job with those execution. So what it does is it calls that API, get the parameter, inject those parameter in the run, and then submit the job to Hadoop cluster. Once the job is completed, fetchers will try to get the data, and it pushes it to MySQL server. Tuning framework uses those heuristics as well as matrices like resource usage, execution time, and wait time from what the fetchers has computed. Based on that, it will define the fitness of those parameters and try to find out the new suggestions for that particular job. So this is how this framework works. So these are some of the features of the framework. So first of all the tuning that run during the regular scheduled runs, there is no extra run that is needed. It all runs in the production itself. Generic framework, basically this framework is generic enough to handle any kind of cost metric, like you can do it for resource usage or execution type or any other cost function. Also, this can handle any framework like Pig, Hive, Spark. So basically, you need to come up with the configuration for different combination and also the constraints for this combination. Once you come up with those, you can feed it into framework and it will start automatically tuning your job. The integration is very easy. There is one API that need to be integrated. And for Azkaban Pig job, we have already done the integration, and that is also part of open source Azkaban plugins. Failure avoidance, as Arpan mentioned, that there are constraints on parameters, so which makes sure that there is no failure. But there are extreme cases where there can be failures as well. To handle those, we have automatic failure handling, which is part of either at the client side or at the tuning framework side. Auto switch off, the same functionality that Arpan talked about is like the tuning switches off automatically if the optimization is already done. So these are some of the features that we are working on. We have already done some POC on the resource usage, as well as some jobs are running in production for Pig. We want to do it for execution time as well. We are working on that. There's one algorithm that we are working on which is called intelligent parameter space optimization. This is for faster convergence. As we talked about static constraints or the constraints on the parameters, those are currently static and are same for each job. But that is not true in the sense that all jobs are very different. Some jobs would be high memory consuming or some might be low memory consuming. So we need to find constraints per job basis. So the IPSO will do it automatically. What it does is basically it looks into the historic executions and look into the counters of those historic executions and come up with dynamic constraints for the algorithm. We already have feature of switch off, but we want to do switch on as well automatically by looking at the current runs and seeing if there is a deviation in the resource usage or execution time. We want to switch on the algorithm. So these are some of the references we have used. Happy tuning. Thank you.
We have time for a couple questions.
Hi, thank you for the talk. So a quick question. So when you try to search the optimal parameters combination, do you rerun the Spark job with different parameter configuration, or how you achieve the optimal configs?
Can you repeat the last part?
I mean, how do you rerun the Spark application with different parameters?
No, we are doing it in the production run only. So all the execution happens. So if you have a daily job scheduled, what the algorithm does is it will try to find out the suggestions, and each run will, so let's say today is one run happening. So we will give configuration with that run. And next day, if some other run is happening, we will give another configuration for the job. So there is no extra run that is done. It is done during the regular scheduled run only.
Hi. So I think your cost function was memory multiplied by the time it ran for. So
Yes.
are you incorporating for the CPUs the job took?
So, but that is basically cared by the time itself. So, in general, you can take care of one of the things, like whether you take care of memory or whether you take care of CPU. If you cannot take care of both the things. This is what we compute is we are based on the memory itself, and all the resources is based on the memory.
But if your job is running multiple CPUs, the cost will go down. So, but it is draining CPU from the other job.
Yeah. So, but then you are saying that if you are using 5 GB of the memory and if you are using 2 cores, then the memory is also divided. Like 1 core is using only 2.5 GB. So if you take care of the memory, it will automatically take care of this cores as well.
Okay.
Do you also consider the amount of data that's running or that's been used on the same process or same program? So meaning if I have the same production workflow, it can run on a smart job or like on a small data set or big data set. So that could change the parameters, right?
Yes, so that is the reason that why we have incorporated a input size in the cost function.
Okay.
So that ensures that, whether the data is small or big, it does not really matter for this optimization process.
Okay, and then these are paired, let's say production or user jobs, or like overall, if I have, let's say at the cluster level, certain jobs with the same parameters, we can use the same optimizations?
No, so this optimization works independently of each of the jobs. It's not for a cluster level.
Got it.
We are joining jobs now.
And then can it perhaps be used for analytics, or is it only for production in the future at least?
If the job is scheduled, if you are, executing it multiple times, then definitely this can be used.
Okay.
The question I have, as you said, they will be daily jobs or hourly jobs or weekly jobs, right? And your framework will define the right configuration for that job.
Correct.
So if I run a one job, right, which is scheduled daily, right? So is it good way, is it good idea to run with the multiple configuration? Ideally, if you run the same job every day, it should be running with the proper optimized configuration all the time, right? I understand the input data can be different, but the configurations, right, it should be run with the same configuration. If you have multiple configurations, you might get, variance results, right, in terms of performance.
So as we have discussed that after 20 execution, the parameter will also converge to a same value. It doesn't keep on changing after that. And once your tuning is, we will switch off the tuning after some iterations. When you reach the optimal configuration, we'll switch off the tuning. After that, we will always return the same configuration.
Okay, and another question I have, if you have 1,000 or 10,000 jobs, we do have the similar situation. If you run the jobs, every single job with different type of configuration, how do you manage the configuration, for all the thousands or 10,000 jobs?
So that is managed in the Dr. Elephant framework itself. Framework manages the configuration. So for each job, as any of the orchestration framework identify it by uniquely. And we have in the MySQL DB for each of the job, what is the configuration for that we have used and what is the best parameter we have found till now.
Okay, so new job will pick it and get
Yes.
the right configuration for the MySQL DB.
Yes.
Right, and will run.
Yes.
Okay, thank you.
We have time for one more question. I think you were next.
Yeah, so for our jobs, we want to minimize the resource usage, but at the same time, we have the additional constraint that our jobs have to finish within 6 hours, or else we'll have production issues. So how do we minimize the resource usage with that additional constraint?
You are asking about the execution
Execution
time,
time.
right?
Well, so our goal is to minimize the resource usage, but
Correct.
we have a constraint that it has to finish within 6 hours, right? Because we need our data to be refreshed.
Yeah, correct. So this is exactly what we had in mind, that we wanted, the goal is to optimize for resource usage, but we had some SLAs that we cannot increase the execution time of a job by this much amount, by let's say 150%.
Yeah.
So what we did was, that was the whole reason of introducing the penalty. So let's say we reduce the resources used very significantly, and it caused a significant increase in the execution time. So although previously with the first version of the cost function, the algorithm will understand that this is a very good configuration set because the resource usage is too low, but we are imposing a penalty, which we are artificially increasing the value of the cost function, so that the algorithm learns that, okay, this is a wrong direction to go, and it takes a turn. And that does not happen again. That is not repeated.